We ourselves, when we made our detections, said extraordinary claims require extraordinary evidence. So we spent a great deal of time understanding everything possible about our instruments, about the astrophysics of the events, about the general relativity implications of the events, to be able to say with confidence to ourselves that yes, this was a real event, and that these two black holes traveling at almost, well, about half the speed of light, collided with each other and produced this little pipsqueak of a signal, all right, you know, billions and billions and billions of kilometers away on our detectors. And I think we were successful, because I don't think that most of the scientific community, in fact, almost all of the scientific community, had no issues with our data. They all believed it too. So what would happen is a gravitational wave has a wave of nature cycle to it. So as a wave is passing by you, what would happen is you would get a little bit fatter in this dimension and a little bit shorter in this dimension. And so that would be the fat you, and then the other half cycle you would get a little bit thinner in this dimension, a little bit taller. That would be the thin you.
I like that.
All right, and then that process repeats itself as the wave passes by you. All right, so right, but remember, we're talking about things that the effects that are 10 to the minus 21. In your case, you wouldn't be able to measure. Your wife, your husband, your boyfriend, your girlfriend, whoever would not know that you were being. They wouldn't know that you were short and fat. So. So we have seismometers and magnetometers and electrometers all over the place to look for strong magnetic fields or seismic events. If there's a person walking by the interferometer, you can actually measure that. If there's somebody playing a song, all right, with a speaker, the speaker, the acoustic waves hammer against the vacuum system, which then transfers that to the interferometer. So the seismic isolation system is, it's an active seismic isolation system where we use seismometers that measure the motion of the ground as a function of frequency. We have them located in places around the floors of our instrument. They take the data, they feed it back to basically a platform that's actually above the mirrors. So the mirrors hang from a platform that's above. And the first stage basically takes that seismometer data and says, okay, the Earth is moving in this direction or in this direction. Or at the equivalent frequency, just inverts that and says, okay, if the Earth is moving like this, all right, then we're going to move in exactly the opposite direction.
Kind of like noise cancelling headphones.
It's exactly what it is.
Right.
It's seismic acoustic, it's seismic cancelling headphones.
4 kilometer long noise.
And then we do that again, and then we put another set of seismometers on that platform, and just to measure the residual motion, and then we feed that down to another seismometer. So we do double cancellation. There's one famous one where we had one of our, the person who runs our facilities, a gentleman named Bubba Gately, all right, take his Harley-Davidson motorcycle, rev it up, run it down, and slam the brakes on, all right, and we didn't see that. I wouldn't have gotten into it if I didn't think it was possible. Everybody who gets involved in LIGO goes through, I think, a period of, well, certainly I did, where you first hear about it and you say, oh, this is crazy. There's just no way you could make this kind of measurement. And then you start studying it and you start reading the papers by some of the people who were really involved early, and you go, yeah, actually it can work. You could actually do it. It's just a question. It wasn't, for me, it wasn't a question of if, it was a question of when. How long would it take for us to detect them? And it took 20 years from my time. I mean, there have been people working in this field, for 40 years that have spent their entire careers working on this. Actually, pretty good.
Really?
Yeah. Well, so I learned about it in the morning. I actually got an email from my deputy director, Albert Lazzarini, and he said, you got to look at this. And he pointed me to a log. We have electronic log books that you can point to, and he pointed me to a plot, and I went, whoa! All right. So my first reaction was, all right, it might not be real. It might be an injection, because we have this campaign where we would inject signals in secretly. So I called up the guys who did that, and I said, please tell me that this was not an injection. And they said, nope. And I said, boom. Right there, I was pretty confident that we had it. But then I started thinking, so by the end of the day, I went home thinking, the world has just changed. we believe we're going to be seeing more and more of these binary black hole mergers. We're really gunning for a binary neutron star merger or a neutron star black hole merger. And as I said in my talk, the thing that would really, I think, be very exciting is if we could catch a neutron star collision in the act fast enough to be able to alert our partners who operate telescopes and have them see the aftermath of that. It's harder, for example, for a satellite to slew, because a lot of our work for X-rays and gamma rays is through satellites, but for optical telescopes, yeah, why not? I'll be honest with you, this is by far, I think, and I hope most people who work with LIGO and gravitational wave business agree with this statement, that this has been the most enriching scientific thing I've ever had the pleasure of being part of. It's a great honor.
Congratulations.
Well, thank you. It's great to speak with you.